So now we're going to move on to look at two studies, one with two data sets. One was with the LSAC and Rakhee and Alison will explain that. And then we're going to have a presentation from Jermaine, and she will explain her data set, which is specific to, it's called KCAT, it's kids with chronic kidney disease. So I'd like to ask Rakhee. Rakhee is, works with us at Menzies at Sydney Uni.
Thanks, Martin, and good morning, everyone. So Alison Hayes and myself are here today presenting work on behalf of our Torch Work Package 3 team. So to address those broader Torch project aims, and some of what Martin was saying is that variable evidence base for psychometric assessment of these instruments, we aimed to identify the strengths and weaknesses of existing pediatric quality of life instruments. So this involved assessing the psychometric properties of these instruments to determine if they measured what they're supposed to. So were they measuring that underlying construct of health-related quality of life in a valid, reliable, and responsive way. So, as we've noted, the lack of robust psychometric evidence may hinder the selection of the right quality of life instrument for the correct context. And then this may lead to issues with accuracy of quality of life measurements and then subsequent clinical and policy decisions. So our evaluation utilized the classical test theory paradigm, and we evaluated the psychometric properties against criteria set out from these best practice guidelines. So what we'll do now is we'll just walk through the psychometric properties that we evaluated in Work Package 3, as well as some of those methods. So starting off, acceptability typically measures the quality of the data. But acceptability can also relate or refer to the feasibility and practicality of using a particular instrument, and may include measures of comprehension or burden of completion. Now, unfortunately, these type of data were not available in the data sets that we looked at, so we weren't able to measure that. But what we did do was measure the data quality. And so what we applied were thresholds of less than 5% for proportion of missing data, and less than 10% for the proportion of serial floor values. Now, reliability assessed how well items on a multi-item scale relate to each other to produce consistent and stable measurement of quality of life. So we measured internal consistency reliability for the quality of life total score scales, as well as any sum scales of the instruments. And we did that using convex alpha and corrected item total correlations with these accepted threshold criteria. Next, moving on to validity. That validity relates to whether the instrument measures the underlying construct that it's intended to measure. And so we looked at convergent validity and non-group validity. So firstly, with convergent validity, that assesses the extent to which there's an association between the instrument under investigation with other instruments that measure the same or similar constructs. So we use Spearman correlations between the total scores for those instruments that were available, and then we categorize the strength of those correlations based on these thresholds. Moving on to non-group validity, what that does is it assesses if the instrument could differentiate between clinically distinct groups. So we hypothesized that children with each of the selected health conditions would have a lower quality of life score compared to those children without that condition. So we use general estimating equations to account for the repeated measures among the same children, And then those separate GE models were constructed using the instruments quality of life, total score as a response variable, and the presence of the health condition as the univariate explanatory variable. And then also what we did was we adjusted for these relevant socio-demographic variables that are known to affect quality of life. And then also reported the adjusted predicted mean quality of life scores with the condition and without. Moving on to responsiveness, what responsiveness does is it's supposed to assess how well an instrument can detect changes in health status over time. So where data were available, we hypothesized that there'd be a change in the quality of life score based on the change in health status over 2 consecutive waves of data. So we evaluated responsiveness using standardized effect sizes and then categorized the magnitude of those effect sizes as well. So Work Package 3 used a variety of data sources that included various pediatric quality of life measures. And today in this presentation, I'm just going to focus on the PedsQL and the CHU9D instruments within the longitudinal study of Australian children, or the LSAC dataset. So as we've also heard, that the PedsQL is one of the most widely used non-preference-based generic instruments to measure quality of life in children. So whilst it does have a relatively good psychometric evidence base, there is limited information about its psychometric performance in children over the whole childhood life course, as well as within the Australian context as well. So Study 1 aimed to address this gap by assessing a standard set of psychometric properties for the PedsQL in Australian children with health conditions across the whole childhood age range, so early and middle childhood, as well as adolescence. So very briefly, the PedsQL consists of 23 items within 4 subscales. So we have the physical functioning subscale with 8 items, and then the emotional and social, as well as the school functional subscales, each with 5 items, noting that the total revision only includes 3 items within the school functioning subscale. And then the PedsQL total score scale ranges from 0 to 100 on a linear scale, and with higher scores indicating better quality of life. So the study was a secondary analysis of the LSAC, which is a continuing population representative survey of children and their families. So it collects data on child well-being and development over the whole life course of the child, and it uses both parent-reported and child self-reported questionnaires. So the LSAC data is collected in phases called waves, which occurs every 2 years using a variety of data collection methods. So PedsQL data within the LSAC included just over 9,000 children aged 2 to 17 years old, with over 50,000 observations for analyses. And also highlighting that the LSAC used the 4 age-appropriate PedsQL versions, all of which were parent proxy reported in the LSAC. So here we've got the prevalence of the 6 health conditions that were included from the LSAC dataset in Study 1. So the highest prevalence was the higher weight status categories, so being overweight or obese, which were assessed measurements. And these were followed by the parent proxy reported conditions of eczema, ADHD, vision problems, hearing problems, and learning difficulty. The choice of these 6 health conditions that were included in the study were based on both a combination of prioritization feedback from our Torch end user group, as well as the availability of the data for the health conditions and the PedsQL for those children aged 2 to 17 years old. So moving on to acceptability results. So PedsQL showed no flaw or ceiling effects over all 6 health conditions and over all age groups. Overall, there are acceptable missingness for the PedsQL for all conditions except in that early childhood age range and for the K cohort in these middle age groups. So what LSAC did indicate was that the data collection method changed to a computer-assisted self-interview method from wave 4 onwards for both cohorts. And so that change corresponded to ages 6 to 7 in the B cohort and 10 to 11-year-olds in the K cohort. And that aligns with the levels of missing data being much lower moving forward than in those previous waves. Moving on to our internal consistency reliability assessment. Basically, it met all the acceptable thresholds for the 4 summary scales, as well as the total score scales for all the conditions over all age groups. However, we did notice that the complex alpha was slightly below the 0.7 threshold for the school functioning subscale in early childhood for 4 out of the 6 conditions, as well as middle childhood for children with ADHD. So now we're looking at the known group validity graphs, and what they're showing is the adjusted predicted mean PedsQL total score. So what we're looking for is a clear differentiation between the total scores for children without the condition, shown in green, and those with the condition, shown in red. So what we see is the ability of the PedsQL to strongly differentiate between children with and without learning difficulty over all age ranges, and for those children with high weight status in the middle childhood and adolescence, but was less consistent in early childhood. So again, we see that the PedsQL differentiates well in children with and without ADHD and hearing problems, where data was available, so that middle childhood and adolescence age groups. The same strong performance was seen for children with and without vision problems, but we do notice that the PedsQL is slightly weaker at being able to differentiate between children with and without eczema. So now moving on to the responsiveness results, so I'll just talk to what we're trying to see on this graph. So we're trying to show the effect size for the 3 categorizations of health status change across 2 consecutive waves of data across those age progressions. So what we anticipate is that there is a decrement in effect size, which is the red point estimates, for worsening change in health status, so such as moving from healthy weight to overweight. And then the purple point estimates, what we're hoping to see is an effect size close to 0 for a consistent health status. So children, say, maybe maintaining a categorization of overweight between consecutive waves of data. And then with our green point estimates, what we're hoping this reflects is a positive effect size for an improvement in health status. So for instance, moving from overweight to healthy weight. So what we expect is this observed trend moving left to right with the red, purple, and green estimates with the correct magnitudes. So what we see for weight status is generally in the older age progressions we see the expected pattern of effect size, but then it gets less consistent in the younger age progressions. Now with ADHD, we sort of see the expected trend for effect size in these younger age groups, but we're seeing very large and overlapping confidence intervals, and then it also gets less consistent in the older age ranges. So we saw similar outcomes for all the other health conditions, where the responsiveness patterns align with the expectations for some of the age progressions, but then was less consistent for others. And also what we found was where we did see the responsiveness trend as expected, those effect sizes were generally small. So from study one, what we concluded is that overall the PedsQL demonstrated pretty good, very good psychometric properties for this range of health conditions over the whole childhood life course in the sample of Australian children and adolescents. So there's strong acceptability with missingness of data being attributed to the change in data collection method rather than poor performance of the PedsQL. And there was strong internal consistency, reliability, and notebook validity for all conditions across all age groups. There was variability with PedsQL responsiveness, and potential reasons for this weaker responsiveness performance includes that actually there were smaller sample sizes for those better, worse categorizations for some of the health conditions, and then also the fact that health conditions and the PedsQL were parent proxy reported. And another potential reason is that except for weight status, which was measured, all the other health conditions were reported either as absence or presence, and there was no degree of severity indicated. So findings from study one align with other international and Australian studies that looked at psychometric assessments of these pediatric quality of life instruments, but it also addresses that gap whereby most of those studies either focused on a single health condition or for multiple health conditions over a limited pediatric age range. So I'll hand over to Alison to talk us through study two. Thanks very much.
Thanks, Rakhee. So just going through study two, the methods that we used here were exactly the same as study one, so I'm not going to go into them in any detail. So in this particular study, we wanted to assess two different instruments. Again, we're using the longitudinal study of Australian children. So we're looking at paediatric quality of life measuring, but we've also looked at child health utility 9D. So the PedsQL, which I will refer to as the PedsQL for brevity going forward, is obviously a non-preference-based measure with scores from 0 to 100. The child health utility is a utility-based measure. It was developed in the UK with children, and it was developed for children aged 7 to 11, but then validated for 11 to 17. In the longitudinal study of Australian children, the valuation used is actually an Australian valuation, and again, it's for children aged 11 to 17. So we were using all the data that were available where the CHU9D was used. Now, it's not in the whole survey because the LSAC started in 2004 and the CHU9D only became available in about 2010. So we used, at the time of the study, we used all the waves available, which was 3 waves of the B cohort and 2 waves of the K cohort, the kindergarten cohort, and the baby cohort is the B cohort. And we had children aged between 10 and 17. And again, we looked at common paediatric health conditions, and the conditions were chosen based on feedback from the end user group and the availability of those health conditions within the LSAC study. So these are the clinical conditions that we looked at, with the exception of weight status. Overweight and obesity were objectively measured. The other conditions were self-reported by the parent, and you can see the prevalence of these conditions in that data set is quite variable. So I'm going straight into the results. So again, we looked at acceptability through missing data and seeing and, got the word. Anyway, we'll come to that. So in terms of missing data, you can see that we've got the PedsQL on the left, and the different waves are up the top, and the CHU9D on the right. And I think you can see that in general, there was more missing data in the CHU9D. In terms of ceiling and floor effects, so floor effects were good for both CHU9D and PedsQL. In other words, they were acceptable at being less than 10%. For ceiling effects, you can see that the PedsQL was acceptable for all conditions across all ages. The CHU9D had ceiling effects more than 10% for most of the conditions and ages. But in fairness, I think you expect when you're on a utility scale that you are going to get a lot of full health records, or one on that scale. In terms of internal consistency, it was really good for both measures. Convergent validity, looking at the association between one scale and another. So normally you would look at, we look at correlation between two different scales. So we have the two different scales. So we would look at each condition. We looked at each condition separately. So children with, let's say, eczema, or children with overweight, and then correlated the scores of the two different instruments. We did actually hypothesize that there probably would not be, that we would only get moderate correlation, because one is proxy-based. The PedsQL was proxy-based, parent-reported, and the CHU9D was self-reported by the children themselves. What we actually found was that correlations ranged from 0.16 to 0.3, so really only very weak conversion validity of those two instruments. Now going on to known group validity, and again, the left is the PedsQL, the right is the CHU9D. We predicted, these are adjusted predicted scores, so we've adjusted for age, sex, socio-demographic status, and cultural diversity. And the predicted, what you would expect is this separation of the scores for children with the condition and without the condition. So on the left, you can see that the PedsQL scores show good separation, in fact, quite a big score difference for some of these conditions of like 10 plus points on that 0 to 100 scale. For most of the conditions, except one, there was good separation. For the CHU9D, there was good separation and good known groups validity, apart from four conditions: asthma, overweight, type 1 diabetes, and epilepsy. Moving on to responsiveness, and I'm not going to present all the results here. This is an example of what you'd expect. This is good responsiveness. So again, we're looking at change over time in a health condition and whether the instrument can note that change in quality of life. So for most of the conditions that we looked at, they were self-reported. So we're talking about movement. If the condition worsens, it's a case of not being reported in one way and then in the subsequent way being reported. And in terms of getting better, it's the reverse. It would be reported in one way and not reported in the next way. Because of the age groups that we had like 3 measures of responsiveness across those different age groups. And so for anxiety and depression, we would say that the responsiveness was good, like when there was no change in the condition, the purple lines line up against the 0. When there was a worse change, it's a negative, in other words, a negative change in quality of life. And if the condition improved, the green ones are on the correct side of the centre line. So just summarising, the responsiveness was variable among the different conditions. Similar responsiveness for both PedsQL and CHU9D, maybe slightly better for weight status for the PedsQL. So overall, I think you can say that they both really have good psychometric properties. The PedsQL, I'd say, was very good. In terms of acceptability, the PedsQL was highly acceptable. It had very low missing data and very low floor and ceiling effects. CHU9D, the missing data was acceptable for 5 of the conditions only, and it did have ceiling effects, but as I said, I think we would expect that with a utility scale. The convergent validity was weak between the 2 instruments, probably because one was proxy and one was non-proxy based. In terms of known group validity, the PedsQL had good known group validities for 7 out of the the 8 conditions that we investigated, and the CHU9D for 4 out of the 8 conditions. So just, and responsiveness. Good for some conditions, not for others. I think limited by sample size, particularly in the sample size of children whose weight status changed. Whose health status changed. I work in overweight and obesity. Health status. Okay, so just summarising the strengths and limitations of these studies. First of all, the strengths, we'll be using rigorous psychometric evaluation using best practice guidelines. We have very large sample size. The LSAC data, which I have used extensively, is absolutely amazing. So we had for study 1 is 50,000 data points. And that's wrong, it's not 7,000, it's like 9,000 children, because there were originally 5,000 in each of the 2 ways. In the study that I presented just now, slightly smaller number of children and data points, but still very, very good. We had a wide range of health conditions. The longitudinal data enabled us to investigate responsiveness, which is very, very seldom reported in the literature. We were able to adjust the known factors, for factors known to impact health-related quality of life, such as age and sex and socioeconomic status and cultural and linguistic diversity. In terms of limitations, we only have the parent proxy reported data for the PedsQL, because that's what was used in the LSAC from 2 to 17 years. The CHU9D data we only had available from age 10 to 17 years. It wasn't able to be used for the earlier ways. And except for weight status, which was objectively measured, health conditions were reported by the parent and as presence or absence of health conditions. Some we weren't able to do full psychometric tests, so because we had existing cohort data, for instance, we couldn't look at comprehension, visibility, the test group test. Okay, implications. So I think we've expanded the evidence base of psychometric performance for these 2 instruments. For the CHU9D between 10 and 17 years, we would say it's good, it's a good instrument. For the PedsQL, we have information from 2 to 17 years, a wider range, and it's very good. Psychometric performance is very good. In terms of economic evaluation, so the CHU9D obviously can be used in economic evaluation to generate utilities, qualities, and cost-utility analysis, but it does have a limited age range, and in Australia, I guess we also have only evaluation for one specific age range. The PedsQL obviously is not a preference-based instrument. At the moment, the only way you can get utilities from it is that are in various mapping studies. But really, what this led to us thinking was the possibility of carrying out evaluation exercise in Australia for based on the fact that it's got good measurement properties over a wide range of ages. It's essentially the same construct across childhood, early childhood and adolescence. So the question set is essentially the same, just a couple of differences regarding school and 21 questions for very young children versus 23 questions for older children. It's also widely used and favoured by clinicians as a generic quality of life measure, so it's actually often used quite frequently in clinical trials anyway. So I think that's all I had to say. Yeah. So any questions on Rakhee? There are publications which I haven't cited. There are publications that Joe.
Hi, thanks. Really interesting. I've got one quick question and a comment, I suppose. So the quick question was just really whether you could tell from the data whether people had been treated with the condition. So, because actually, if you have treated something like eczema, then you maybe wouldn't expect to see big changes because somebody had the condition. So that was my question.
Yep.
And my comment was, I think we need to be really careful about drawing conclusions about the instruments from what you're able to say, because you could equally use it to draw conclusions about whether self-complete or proxy makes a difference, or whether using a utility score versus a non-utility score makes a difference. So I think we just need to be really careful about that.
Completely agree, and I didn't want to, we never saw this as a head-to-head study. It was just two instruments in the same group of children, the same data set, and assessed against psychometric properties. We never saw it as a head-to-head. Your quick question, I don't believe we do have information about treatment or not for those conditions. Rakhee, do you know?
No, it was just reporting, reporting absence of presence. There was no indication of whether it was being treated. So again, constrained by what we're actually able to get from the data set.
I have two questions. One, with the self-reported element, have you looked at any population data to compare if it's comparable? So particular, for example, like the hearing problems, 2% is very high depending on how you define hearing loss. So bilateral sensorineural hearing loss is normally about 1 of 2 in 1,000 at age 5. So 2.2% is very high from a self-reported measure.
So I don't think I think it was quite a broad hearing problem, so it wasn't necessarily hearing loss. So yes, do you know how it
So
compares
basically,
to?
the definition of hearing loss may not be comparable with, say, technical, clinical definition of hearing loss, because it was just parents self-reporting absence of presence.
Because that might affect the
Yes,
how
the prevalence.
Yeah, but it also might affect whether it's reporting or not, because if it's a sensory neural hearing loss, you shouldn't see any change in responsiveness. You can't treat that technically. And I guess that's the other question I had is, what about conditions that once you're diagnosed, you actually can't cure them as such? So you shouldn't see that on the responsiveness, right? So for example, type 1 diabetes, it should only just increase as other people are diagnosed. Is that?
That's right. So when we did do the responsiveness, especially with CHU9D and LSAC data, those categorizations for the likes of type 1 diabetes, I can't remember the other one as well, but we only looked at worse or the same categorizations. We didn't categorize anything as better because exactly that's possible.